So let's get a little bit closer to the definition of loop bandwidth. So let's say got this picture of your op-amp circuit over here. And let's say that your op-amp, so the thing inside the green circle, maybe draw it with green, your green op-amp here. Let's see if you say that if you tested it and you plotted it on a Bode plot, let's say it just has 20 log of gain. Should put absolute value. I haven't been putting absolute value on that. 20 log of gain, and then out to, actually, let me draw this differently. For the underlying op-amp, your its gain is probably extremely high. When you have a high gain, often you have a low bandwidth, and by bandwidth, I mean where its first corner is. That might be at kind of a low frequency. Okay, so that's the underlying op-amp. That's just your op-amp, and you're taking your, if a differential signal, you've got some sine wave here, and you've got equal and opposite sine wave on the inverting input, and your amplitude of your output from right here, it starts to drop. Okay, whatever this frequency is here. So that's your underlying amplifier. What happens when you hook it up with feedback, so feedback will, again, if you remember that your total gain of your op-amp with feedback is whatever the gain of your op-amp is over 1 plus AVF, which is just the loop gain. So your gain of your amplifier gets decreased by this factor of 1 plus T. Okay. So once you hook up with feedback here, whatever that feedback might be, now what happens is the gain decreases by a factor of 1 over T. So over here someplace, now you've got 20 log of your original gain, whatever that was for the op-amp without feedback, that all gets divided by 1 plus T. And what happens is your gains, you know, at your new value that you've set your two resistors here such that you get some specific gain. So that gain comes out here and goes across until it hits the underlying op-amp limitations. You can imagine that you can't go faster than the fastest that any of your components can go. So if one component can only go up to 1 kilohertz and another one goes up to 2 kilohertz, it doesn't matter that you have one that can run at 2 kilohertz. The 1 kilohertz one is going to limit your performance. And that's what happens here. The underlying op-amp can't have a gain out here. Remember, this is frequency here. So with a single op-amp, you can't get anything on this side of this line. You can't do with this op-amp, because the op-amp is almost a boundary of possible performance. You can do anything to the left of that line, but you can't do anything to the right. So what happens when you hook it up with feedback, now you've got your new gain, and it keeps it at that gain until it hits the underlying op-amp limitation, and then it follows the line down. Okay, up here, this has a very narrow bandwidth. So the bandwidth is the up to what frequency do you get a constant flat gain? Okay, that your gain isn't changing. So this is called bandwidth this is your bandwidth, and it goes to wherever the lowest frequency pole is. Okay. But when you hook it up with feedback, this neat thing happens is that that gain, whatever gain you've set your op amp to behave to give you with the feedback network that you set up, that goes over until it hits the limitation by the underlying op amp. And what you'll notice is, because your gain is dropped, this will always be a wider bandwidth. So when you drop the gain, the bandwidth is higher. And that's called widebanding. So you drop the gain, and by dropping the gain, your bandwidth, in other words, the region where you have a constant gain, increases. It gets broader, it gets wider. Okay. So we've got the bandwidth of the underlying op amp. You see that if you hook up feedback on your op amp to get a specific gain, you get a wider frequency. What's interesting is how much wider this is. Let's say this total gain right here, so the gain over 1 plus your loop gain, let's say you have this set up. I should probably draw a new graph just to keep it pretty. Let's do narrow band like it is up there. We've got that, and this is your 20 log of gain. So this is still magnitude. This is still a magnitude plot, and this is still frequency plot here. And you come over here. Let's say you have a gain of, you've set your resistors for a gain of 100. So let's say you have a gain equal to 100. And let's say that gives you, so let's say this was 1,000,000 or something, or 10,000 or 100,000. So that would, your 20 log of that gain come out here, and it would follow this down. Okay, let's look at a different case. Let's say you have a gain of 10. Now that gain is lower, so you're going to get a wider band. I'm going to go down here. But let's look at this. So that's your F2 for the gain of 10, and then this is your F1 for the gain of 100. Okay, so let's look at this. If you take 20 log of gain equals 100, and this 100 is with the 1 plus t, so it's this gain over 1 plus the loop gain gives you 100. So if you take 20 log of 100, that's 10 squared, so you get 40 dB. So this is 40 dB. Okay. Now, here, again, this is your gain of 10. So if you have log of 10, that's just 1. So this is 20 dB. So I've dropped by a factor of 10, basically a decade. I've dropped the gain by a decade, and you notice that the dB that you get is 40 dB. You notice the slope of this line right here is minus 20 dB. Per dec. So what happens is, you know that this point right here is 40 dB, and this point right here is 20 dB. And you know there's a slope of minus 20 dB per decade. So these two frequencies right here, those are a decade apart. F2 equals 10 times F1. And look at the gain. The gain went from 100 down to 10, but the frequency went from F1 to 10 times F1. So let's look at that. Let's look at what happens if I multiply the gain times this frequency. So here for gain equals 100, for gain equals 100, gain bandwidth, in other words, gain times your frequency, that equals 100 times F1. Okay, now for gain equals 10, your gain bandwidth product, it's often called gain bandwidth product, that equals your gain, which is 10, times your new frequency, which is F2, but F2 just equals 10 times F1. And you can see that you still get 100 times F1. And that will happen with any gain that you give this. If you take a line across, you take your gain. Remember, this the value on the y-axis is 20 log of this gain. But if you take your gain, so the thing inside the log, and draw a line across and then down to find a frequency, the product of that gain, not 20 log of the gain, but the gain itself, times this frequency, it will always equal 100 times F1. Okay. And that's the gain bandwidth product. So if you have a single corner, and we've already seen how you can find a corner inside a op amp. If you have a single corner system, and in this case, you'd assume that the secondary secondary pole, dominant pole, secondary pole, assume it's far enough out that you can you have space here to where you have a constant, you have a nice space here that's minus 20 dB per decade for a good area here. Okay. So the gain bandwidth product, it gives you gives you this value anywhere on this line. Again, if you take the gain and multiply it by the frequency, you'll get a constant. You'll get this 100 times F1 in the example here. And what this gives you is the manufacturer doesn't know what gain you're going to set this up for. Doesn't know what R1 and R2 you're going to pick. But you may have a specific gain you need, maybe 23.5, and somebody else needs it to be 700. For both of you, you come over here and you say, oh, I need 23.5 gain. And you say, well, I know the gain bandwidth product is 100 times F1. And you can figure out F1 actually. 100 times F1. And I know that's the gain times my frequency. And I know my gain is 23.5, for example. And I want to know what my bandwidth will be. Instead of writing F here, I probably should write bandwidth. And that will tell you this frequency right here, if you solve for this. Okay. Yeah, I'll stop here. There was something else I was going to say, but I'll stop here.